In astronomy, finding exoplanets is a very important aspect, and one powerful tool that astronomers use is transit photometry. The idea is to stare at a star for as long as possible, measuring its light levels at every possible instant. Then, when an undiscovered planet were to pass in front of the star in observation, the light levels will dip a bit. Measuring the percent of light loss when the planet transits the star, we can calculate how large the exoplanet is. When we put all the light values onto a graph, we create what is called a transit light curve, which we then measure the depth of that curve to plug into an equation, which is the exoplanet's radius is equal to the star's radius multiplied by the square root of the depth of the curve, also known as the percent of light loss during the transit. This method has been proven to work, with about 4,128 exoplanets being discovered using this method. The TESS satellite, or Transit Exoplanet Survey Satellite's job is to stare at stars for as long as possible until a transit might occur. In this video, I will conduct an experiment with a flashlight, a light measurer, and a solar system model. The idea is that we shine the flashlight, turn that on. The idea is that we shine the flashlight onto the light meter and measure the light. Once we've done that, we take one of these model planets and pass it in front of the flashlight. The flashlight is meant to represent our star, this is meant to represent an exoplanet, and this is meant to represent a satellite. And then once we measure the light dip, let's see if we can calculate the exoplanet, in this case the planet's model's radius, and then compare it to real measurements of it and see how accurate it is. Okay, let's begin test number 1. Okay. We are using a solar system model I got as a gift, each with different planets, and then my cat. So yeah, there's a headlight used for camping onto a tripod, and there's a lux meter. Hopefully this is accurate. Hopefully, if it's not, we can change it up. Let's begin. Already pitch dark. Okay, let's use Mercury. Hello, cat. Okay, let's begin. And then okay, no, Mercury's too small. How about, oh, my cat's moving it. Okay, current number, wait for it to slow down, 1670. That's basically, I'm gonna move this over the light, and let's begin. That was kind of scattered. Okay, now let's do the math. So we know that the starting value of the light would be 1,670. And then we know that when the planet passed by, it equated to about it dropped to about 1,260. So now we have to calculate what percent of 1,670 is 1,260. So we divide 1,260 divided by 1,670, which gives us 0.754, or about 75.4%, round down 75%. And now, so we just take 75%. Now we gotta calculate how much of that dropped, how much the light dropped down by percentage. So 100%, the total light value, subtracted by what it dropped down by, so 75% equals to 25. So it dropped down by about 25%. Now, the way the formula works is we get the square root of that value. So the square root would be 5, obviously. And then we multiply that by the radius of the star. In this case, it'd be our flat headlight. And I measured it with a ruler. It was the diameter was about 24 millimeters. And so since the diameter is twice the radius, it would be 1.2 centimeters. So we divide it by 1.2 with 1.2. But remember, we have to use the unit, which is the correct unit, which is meters. So 1.2 centimeters is 0.012 meters. So 0.012 meters would equate to... Okay, I have realized my mistake. So we got the square root of the percent drop down, and then the value, which is 0.012 meters. I realized I divided it, not multiplied. So multiplied by 0.012 would give us a value of 0.06. And so if we convert this back to centimeters, this would be about 6 centimeters. Alrighty, so now after we measure this Mars model using a ruler, try to get a rough estimate, we measure that, it gives us a value of 1.2 centimeters. So the diameter from each side is 1.2 centimeters. Now the radius is half of the diameter, so the radius is 0.6. Now we can see I wrote that down for Mars using the ruler, and the equation to calculate what the radius of the planet would be gave us 6 centimeters. So we can see that there's a relation to this. The actual measurement of Mars's radius is 0.6 centimeters, so 6 millimeters, but the equation to calculate Mars's radius through the transit photometry through this method of detecting exoplanets, it gives us a value of 6 centimeters. So we can see that they're proportional, so 0.6 and 6, they're proportional, but one of them is scaled up to 10. So we're just going to take note of that. So this equates to that times 10. So yeah, let's just take note and conduct some more tests. Now, one reason why I love this method of finding exoplanets so much is that the values are proportional, and it's pretty accurate. So it doesn't matter, like, depending on the stars, the value of the light is always proportional. Okay, so in this case, I would be using a Neptune model. I think it's like the fourth or third largest planet. Doesn't really matter. And let's take a look at what the value is right now. Wait for it to slow down. Okay, the value is really fluctuating. I don't think this is a good software or a good method of measuring light, but it's all they got. So I'm just going to say 1,420. And so if we were to pass it through, let's get my camera up here. Oh, it dropped again. Okay, 1,350. Let's pass it through slowly, like an exoplanet would, and let's check. Okay, it's a new day, and I just got a new idea. So yesterday we realized that the equation was 10 times the amount of the actual answer. So if the actual radius of an exoplanet was 6 millimeters, and the equation would have given us 6 centimeters. But I think I know why. Now, when we calculate the equation, it tells us to find the depth. Now, I always put the depth as a percent, so like 42. But maybe it's an actual percent, so like 0.42. So let's try that out. For example, in test 1, the starting value was 1,670. The depth was 1,260. We get the percent of that divided by 1,260 divided by 1,670. So 75%, 75.44. Now what if we do 1 minus 0.754 equals that, and then we get the square root of that. So we do not like multiply it by 100, we get the square root of that. Then we multiply it by the lens value, so 0.012 meters, which gives us precision. That would be 6 millimeters. Basically 6 millimeters. Let's go. Okay. I've gotten the old lux meter back. And let's conduct some tests. I think I'll do 3 more before coming to a consensus. So this is test number 6, actually, because test number 7, because test number 6 was inaccurate. Okay, we're gonna use Mars again, just like we did before. And yeah, let's get straight to it. Okay. Lucky I live in Canada. And the sun is down when it's like 4 actually. 5 or something, I don't know. Okay. I'll just assume 1480. Yep, okay, let's pass it through. Okay, let's take a look. Okay, so it started at 1480. And it dropped down to 1150 after I checked the video. So do 1150 over 1480, which gives us 7777. Okay, now we have to multiply. Now we have to add this to 1. So I think we can just do this by turning this negative and then adding 1 to it. Which gives us, we did it. Okay, so 22%. It dropped down. The light dropped down by 22% when the Mars passed by. Now, let's square this. So so that, and then we multiply that by 0.012, which is the radius of our star, also known as my flashlight, which gives us 0.0056, or just 6 if you want to be rounding. After conducting multiple tests, I have come to the conclusion that exoplanet transit photometry is a really efficient method. And I think the technology that is behind this is one that could change our understanding of our universe. So I feel that this is one of the most important technologies in the space industry, and I believe that we should continue to take advantage of these scientific technologies to further our understanding of the universe. Although we did see some inaccuracies with some of the tests, I put that up to my equipment that I use, and it is not professional. It is just whatever I have on hand. So I feel that with the proper equipment and with the proper technology, transit photometry has the ability to just allow us to discover hundreds of thousands of exoplanets and millions of new worlds out there. And I feel that we have to continue to use these technologies. In all seriousness, even though this test was a little bit scuffed with not the best materials, I feel that this still helps us understand how these technologies like exoplanet photometry works, and how satellites like the TESS satellite works in space, and how it finds these exoplanets. And yeah, I hope you guys learned something from this video, and I'll see you guys next time.